Okay, so here's where we were last time. Well, here's what we left, what we were about to start talking about last time, integrals and spherical coordinates. We already did, let me just remind you, we did talk about integrals in polar coordinates. And we did talk about integrals in cylindrical coordinates. So integrals in spherical coordinates, you could probably kind of see how this is going to work. So the pattern is very strong. We observe that the change of coordinates formulas can be reinterpreted as a change of variables function. Right? We have rho phi theta world over here, and then we have XYZ world over here. Right? And we can think of those change of coordinates equations as being a function that goes from here to there. Okay. You can compute the stretching factor. It's the same formula that we used for the previous coordinate system integrals, and here's what you get as a punchline. It's the absolute value of rho squared sine phi. Now this is a good exercise, and I want everyone to do this. Right? Fill in the blanks here on the dot, dot, dot. It's just a little bit of, a couple of partial derivatives and a determinant. And then you do have to invoke the Pythagorean trig identities a couple times. I want to say 3 times. It's been a long time since I've done this. But I have done it. I did mine. Now y'all got to do yours. Everybody should do this once in their lives, right? It's not that bad of a calculation. It's about a half a page. But it's instructive, and everybody should do this once in their lives. And like I say, I did mine. Make sure to remember this formula. Now you see those absolute values. Nobody likes absolute values in their integral. Can we negotiate around some way to make sure that we can lose the absolute values? And the answer is yeah, sure. Just make sure that this is always positive and you're good. Now, notice rho squared is always positive already. That's not an issue, right? The issue is with sine phi. We need to make sure that's positive. And the way we ensure that sine phi is positive is by requiring phi always be between 0 and pi. Now that's a thing at this point, right? This is a constraint that we have to obey. Henceforth, when you're doing spherical coordinates, at least when you're doing spherical coordinates for the purpose of spherical coordinate integrals, you are required to choose these values of phi that you wanted to choose anyway. Again, I'll point out, these are the natural, like 0 to pi, right? I mean, that's the way you want to think about phi, measured off of the z-axis, of course. It gets weird when you think of values of phi outside of that range. These are the easy ones. This is what we want. So, it's one of these weird situations where everything just lines up just perfectly. You know, if you do what you want here, then you also get to do what you want over here. Right? So, it's a no-brainer. Always do this. There's just no reason not to. Okay, so this is the formula that you're going to memorize for your stretching factor. It's rho squared sine phi. Make sure to memorize that. Yeah. So technically we have everything that we need now to do a pullback. If you have some domain on the right, whatever that might be, whatever your solid is on the right, you can do a pullback. I don't know, look like something like this over here in the rho phi theta space. And just like with polar coordinates, just like with cylindrical coordinates, I suppose if you really want to, I suppose you could start slicing up with, row slices, etc. You could do regular old slices of the pullback domain, but why would you? You can see what those slices look like over here in XYZ space, right? This is what a theta slice looks like. It represents a constant value of theta. There it is. That's what it looks like. This is, let me get rid of the thing. This is what a constant value of phi looks like. Keep in mind, phi is the angle as measured off of the positive part of the z-axis. So if you set phi equal to a constant, you get a little cone, which I'm going to confess is a weird way to slice, right? I mean, I don't have any knives in my kitchen that cut like that. But anyway, nevertheless, that's what a phi slice looks like. And then continuing, this is what a rho slice looks like. It's a sphere. That's what you get when you talk about constant values of rho. Why would you pull back all the way over here into rho phi theta space when you can just as easily just make the appropriate kinds of slices and then deal with the domain you already have in XYZ space. It's much nicer. Okay, that said, good news. It's not as curvy and weird as this would suggest. If you make this choice for the order to do your differentials, if you always do your theta slicing first, right? Notice that theta slices are nice and flat. Your phi slices second. Now, phi slices are kind of curvy and weird, except for the fact that don't forget, we're not slicing. We're not going to do phi slices of the original solid. We're going to do phi slices of our theta slice. And the way that phi cone intersects our existing theta plane is in a line segment, also flat, right? Which is nice. And then lastly, our row slices. Do row on the inside, or said differently, do your row slicing last, and then you're just looking along this segment for starting and then somewhere ending values of row, and everything is nice and flat. I mean, it's angled, right? It's angled, but it is nice and flat. Okay, so it is, remember how I told you, it's usually almost always the case with cylindrical coordinates that you're going to pick one of these orders right here, right? Keep your r and your theta together, and then do z either, on the outside or on the inside. That's pretty much the only reasonable choices for cylindrical coordinates. For spherical coordinates, it's always this one. So, don't even entertain other choices. It'd be crazy, crazy weird. Very, very unusual. I'm sure I could construct a counterexample, but in this course, you're not going to see any counterexample. This is always the way to do it. Okay. Lastly, don't forget your stretching factor. One of the most common mistakes that I see students make. Very important mistake. It's wildly inaccurate to do a integral in spherical coordinates. If you don't put that stretching factor in there, you're making up nonsense, right? So it's not just that missing this factor will give you a wrong answer. It's that missing this factor makes it look like you believe in nonsense. It's really bad, right? So it's essential that you remember it. And along those lines, really good memory tool is to always write it down all at one moment, right? In one fell swoop, write down this whole thing. Don't ever write the differentials down by themselves. There's no reason to do that. Why would you do that? That doesn't make any sense at all in any context. It's silly, right? So, deep breath. Rho squared sine phi d rho d phi d theta. Write it all down all at once, right? And if you follow that rule, if you adhere to this constraint, always write it down all at once. That'll cut down on you forgetting to do it at all. Okay. Alrighty. Well, let's go and do one. Suppose you want to do an integral over this ball. All right, so, and I emphasize this is a solid ball. Don't forget the word ball means solid. If you want to talk about the surface, then you say sphere. Here we are doing the solid, so here we're doing an integral over the ball, right? This three-dimensional ball. You could do that in rectangular coordinates. I'll remind you, we've done integrals over balls in rectangular coordinates, and there's square roots everywhere, and it's ugly and highly undesirable. So we're going to see how this plays out in spherical coordinates. And remember, we are in fact doing a pullback, right? But the way we're going to actually realize that pullback is to look at the slices, like this tells us. Don't forget our stretching factor, and off you go. I mean, that's the shortcut of the pullback. So, okay, so here we go. Here's our solid. And let's start taking slices of our solid. Theta slices. What's a theta slice look like? Well, here it is. That's a theta slice. Now I appeal to your geometric intuition. By the way, that's unavoidable. This is heavily geometric. There's no way around the geometry here. There's no sort of like I'm just going to do an algebraic version to figure out my spherical bounds. This doesn't work. Right? You got to see the picture. You have to understand the picture. You have to deduce from the picture. From the picture, as I see here, think about what happens. You've got this ball centered on the z-axis. You look at these half planes hinged on the z-axis, and I appeal to your sense of geometry. These go all the way around 0 to 2 pi. You got to see it from the picture. Okay, are we good with that? Everybody see the? Yeah. Okay. If you have trouble visualizing these things, you can get some Play-Doh, right? Seriously, and Play-Doh and a putty knife, right? And you can literally slice up your Play-Doh, or you buy a sack of oranges. Right? Everybody should be eating more fruit anyway, right? It's a win-win, right? You get a sack of oranges and just, cut it up and see what these slices look like. Okay, so theta goes from 0 to 2 pi. Now, we are going to, for the remainder of this question, focus our attention on the theta slice. That theta slice looks kind of like this. And I say kind of like this because, my picture is not perfect. Drawing three-dimensionally is hard, and being competent at it doesn't mean that your pictures are going to be perfect. And plus, who needs the challenge, right? So here's what I'm leading up to. Strong advice. What I suggest you do is, after you've figured out your theta bounds, take that theta slice and redraw it. Looking at it, what I'll call kind of edge on. Looking at it straight on. Right? So in other words, if I were looking from that direction, right? It's easy to see that this is what a theta slice would look at as seen, from that angle. And it's easier to draw. And you can represent more clearly, like what's going on down here. Well, that's part of a semi-disk, right? And so you can see more about how that edge, it goes to the origin, but at the origin it's tangent to that R-axis, you might call it, right? You can just see that better than here. That picture, kind of hard to tell. A little bit harder to interpret from. Okay, so you don't have to, but I strongly encourage you. Draw your theta slice like that. Now, with the theta slice drawn, it'll be easier to see what your phi ranges are. Now, you could, I suppose, see it over here. You could see these are phi slices, but if your picture is poor, you might think, it kind of stops there. I don't know, that looks like about pi over 3 or something. It just, if your picture is mediocre, you might just get the wrong idea. Whereas, over here, looking at this straight-on picture, it's just easier to see that these phi slices keep going until you hit that line there tangent to the R-axis. And it's just a little bit easier to see that your phi values go from 0 to pi over 2. Yeah? All right. Now, yeah. Okay. So, lastly, then we've got to figure out what are our row bounds. Here is a phi slice, specifically a phi slice of our theta slice. You can see where that You can see where that intersection is. Right? Is that? And you can see right here on the picture that there's the point that determines my starting value of rho. There's the point that determines my ending value of rho. Yeah, but what are those points? Where is the ZR plane? What am I looking at here, right? It's easy to kind of lose track of what you're looking at. So don't forget what those really are. Those are, back here, there's my phi slice of my theta slice, right? Those 2 points are there and there, and you can see more easily, I think, perhaps from this picture, you can see that your starting value of rho is, there it is, it's at the origin. That point's at the origin, and rho at the origin, 0. Right? Your ending value of rho comes from that point. What do we know about that point? Well, that point's on the sphere. Right? And so to find my upper value of rho, I need the equation of that sphere, and so you've got a spherical equation problem. Flashback to section 12.8. How do you write the equation of the sphere in spherical coordinates? Okay, so you can see those showing up in these eventual bounds that I have down here. Theta goes from 0 to 2 pi. For any given value of theta, phi goes from 0 to pi over 2. And then on my phi slice of my theta slice, rho starts at 0 and ends, well, again, you got to find the equation of that sphere. Make sure you can do that. That's the equation of that sphere. I'll give you some reminder tips in just a moment as to how to do that. But with the equation of the sphere, solve for rho, and that gives you your upper bound. Okay, so how to find the equation of that sphere? That's no big deal. The sphere in rectangular coordinates is x squared plus y squared plus z minus a squared is equal to a squared. There's the rectangular equation of that sphere. And then plug in the conversion formulas, simplify, Pythagorean identities, etc., etc. And again, it's a 12.8 problem, but that's how you get started, and you go through and rewrite in spherical coordinates, and you will get this, aka that. Everybody see the process? Doesn't it look familiar? Really, really smacks of cylindrical coordinates, just different shaped slices. Right? Different kind of slices, but it's still morally the same idea. And let me call your attention also, don't forget, you've got to rewrite your volume form. Right? dV. I just made the big mistake. Right? You got to be really careful about that. Your volume form, don't just write down d rho d phi to theta. That doesn't make any sense. It's not a thing. It doesn't have anything to do with the problem, right? The volume form is this whole thing. You see how easy it is to make that mistake? I did that on purpose. You see how easy? Don't forget that stretching factor, rho squared sine phi. Really important. Really easy to forget, but really important. Side note, in case you're curious, my experience shows that my making a huge deal out of don't forget your stretching factor cuts down the occurrences of students forgetting their stretching factor from about 20% of students to about 10% of students. Right? So some students will still forget. So don't think you got this knocked. It is a serious problem. It is so easy to just, I can't believe I forgot my stretching factor. Don't let that be you. Okay, some more examples. I'm going to go a little bit more quickly because we're behind schedule, and because the pattern is, it's all the same, it's just different geometry in these different examples. Suppose this time that the ball is centered over here on the y-axis, described by that algebra. Think about your slices. There's what a theta slice looks like. This is geometrically a little bit challenging, right? To think of, how those look. Notice those theta slices are not always the same size, right? When you're looking at a theta slice way over here, it's going to take a real thin slice off the side of that ball. Again, buy a sack of oranges, right? Take a sack of oranges and then think about, as you turn the knife, centered on the z-axis, right? I emphasize we're not centered on the center of the sphere the ball that we're looking at. We're not doing that, right? The axis is the z-axis, so you're kind of centered on the sort of the edge. And just notice that when you're, for sufficiently extreme values of theta, you're not getting a slice out of the orange. You're just getting that little bit of zest. Right? Just that little surface, just a little bit. And as that angle changes, you're getting thicker slices, and then on the other side, again, just that little bit of zest, thinner slices. So, our first zest slice over here at theta equals 0. And then our last little bit of zest slice is over there at theta equals pi. So 0 to pi. Got to see it from the picture. It's all about the geometry there. Yep.
So is the edge at the origin?
Yeah. That's right. So that's right. So the center here is you can see the center is 1 on the y-axis, and then the radius also 1. And so that the edge is right there at the origin. That's right. Yep. That's right. Okay, so 0 to pi. Now we focus our attention on a single theta slice, like so. Here it is. Easier to draw over here, right? It's tough to draw a circular slice at an angle. This is weird, right? But it's really easy to draw it looking straight on. It's a disc. Nothing to it, right? Easy picture. Right? So I'm a big fan. I hope y'all will take my encouragement to don't do that. Do this. Okay. So on that slice, let's think about the range of values of phi. Well, there's a typical phi slice. Lower values of phi, greater values of phi, and altogether, the first one, small though it is at 0. The last one is at pi. 0 to pi. Again, you gotta see the picture. Okay, and then we gotta think about the values of rho. A very similar deal to the last one. Here's the point that determines the starting value of rho. It's a way of visualizing that point. That point is, look, you can see it from the picture. It's the origin. Rho is equal to 0 there. No problem. The ending value of rho is going to be determined by that point. That point, well, yeah, but that's actually this point. Right? It's a point, therefore, that is on the sphere, and I'm going to have to solve, find the equation of that sphere again, and solve for rho in the equation of that sphere, and that will tell you that upper bound for rho. So again, you got to write down the equation of the sphere. Here it is in rectangular coordinates, and then convert to spherical coordinates. And in this case, it gives you this, which you will see motivates our upper bound for rho. Rho squared sine phi d rho d phi d theta, right? Written down all at once. Don't forget that stretching factor. Super easy to do. And here's the other bounds. We already agreed theta went from 0 to pi, and that phi went from 0 to pi, and there we are. Spherical coordinates integral. Okay. Last example, I put in here mostly because the drawing is hard, and I just kind of want to point out some tricks about the drawing, and that is to set your expectations low. Right? Don't expect that you can draw something so well, even when it's so hard, that you're just going to be able to see every single thing from just that one picture. It's just not a realistic goal. Right? So anyway, here's what we're trying to draw. We're looking at the collection of points that are, notice the inequality here, outside of the unit sphere. Right? And yet, at the same time, points which are inside of this other sphere centered at 1 on the z-axis and with radius 1. Right? So inside of that sphere. So now again, you're going to think about the picture. We're looking for, we're looking for the part of that green ball that's chomped out by that yellow bite. Right, and so all together then, what we're looking at is, and this is where this drawing starts to get bad, but we're looking at kind of that thing. Now let me criticize my drawing. This drawing suggests, as I have it drawn here, it suggests that we have a little corner there, but we don't. We don't have a corner. What we have is there's actually a sort of a lip, right? There's a little lip that goes all the way around here. Right? Imagine an actual ball, and then there's an actual, like an ice cream scoop, a melon ball or whatever, that's taken a sort of a scoop out of the bottom of it, and that creates a lip that goes all the way around. It doesn't have a vertex. There's an edge, but it's I mean, how do I draw that without making it, I don't know, it's hard, right? So accept imperfection, and then just use, you got to use your imagination. Don't forget that there's actually stuff, there's actually stuff in there as well that I think it, drawing it makes the picture worse, not better. Okay. Nevertheless, I think still pretty clear that theta, looking at this solid, theta still goes all the way around 0 to 2 pi. Right? Here's where drawing the cross section separately really is a big win. If we look at this theta slice, that's going to be really hard to draw here. This is a bummer of an art challenge to draw that. But it's a lot easier over here as follows. If I think about how does that theta slice intersect this ball, that's easy. A slice of a ball is a bit of a disc, right? It's a half disc. How does it intersect with this ball? Well, that's another half disc, right? I'm looking for the part inside of the green, outside of the blue, right? So the slice of that solid inside of the green, outside of the blue, well, it's going to be what I see over here. That's inside of the green slice and outside of the blue slice. So it's that right there. Right? So this is a weird sort of geometric example where it's actually arguably easier, if you take this point of view, right? It's easier to draw the slice of the solid than it is to draw the solid itself. Stuff works out weird sometimes. Okay. All right. So let's look at phi values and row values. Phi, our phi slices, right? There's our first phi slice. Here's what our phi slices continue to look at. That last phi slice is going to happen, wherever that point is. Clearly, I think it's pretty clear anyway. Phi slices start at phi equals 0. Right, but that last one, what's going on at that point? Well, this is another one of these situations where we have an equilateral triangle. Now, you got to think it through. Details for you guys, right? We saw an instance last time in doing a polar coordinates problem where there was an equilateral triangle that allows you to determine an angle. There's a very similar deal here. You need to persuade yourself that actually is an equilateral triangle. Think it through. How do you know? Right? What are these three edges? How do you know they're all equal? Having done that, that value of phi is pi over 3. Okay. All right. A given phi slice row starts at that point. That point's on that curve. That curve came from this sphere, which has that equation. It's pretty easy to convince yourself the starting value of rho is 1. Okay. The ending value on that same slice, the ending value comes from that point. That point's on that curve. That curve comes from this sphere, which has that equation. Solve for rho. Now again, here's another one where you got to do some algebra, right? You got to write down there's the rectangular equation. You got to convert it into spherical coordinates and solve for rho. Details for y'all. But this is what you get for the upper bound for rho then. Okay. And put it all together. Here's your integral. There's the bounds that we just went to a bunch of trouble to identify. Don't forget rho squared sine phi d rho d phi d theta. Again, written down all at once, all in one fell swoop, because it doesn't make any sense to write down the differentials by themselves. That's not a thing. So if you write it down all at once, you won't forget it. And there's your integral, and off you go. So that's integrals and spherical coordinates. There's lots of examples to look at. There's several in the book. There's several in the exercises. Give yourself plenty of practice on drawing these pictures and analyzing the geometry. Okay, so moving on now. New topic. Still in chapter 14, but to be honest, we're now getting really close to chapter 15. Getting really close. One could argue that this is really more closely connected to the chapter 15 material than to the chapter 14 material that we've been looking at. So, depends on how you look at it. So, new question I want to entertain, and that is, suppose you've got some sort of an application problem. Let me remind you, why do we do integrals? We do integrals because we want to compute masses of things, or we want to compute the amount of work it takes to do a certain task, or we're trying to compute how many ants there are, or how many bacteria. Right? We're adding things up. What I like to call chop it up, add it up, which y'all may recall. Right? Okay, well, we've talked about if you have an interval on the x-axis, chop it up, add it up gives you single variable integrals. If you have a two-dimensional region in a two-dimensional plane, that gives you double integrals. If you have a three-dimensional solid in a three-dimensional space, that gives you triple integrals, right? And then everything we've done since talking about triple integrals has really been kind of computational techniques for how to compute these double and triple integrals. So now we're going to go back to making integrals, making new kinds of integrals, and here's the weird question. What if your domain is what I will call dimensionally awkward, right? Not a two-dimensional thing inside of a two-dimensional space. What if you have a one-dimensional curve, but that lives inside of a two-dimensional space? You're going to do that with a double integral? Doesn't make any sense. Double integral doesn't make any sense at all in this context. So if you chop this up, you don't get little pieces of area. You chop this up, you get little pieces of length. Right? So this is not a double integral. It just fundamentally isn't. And yet, it's also not a Calc 1, Math 111L integral either. Because the domain is simply not, on the x-axis, interval from A to B. It just isn't. Right? So, what do? Answer? We don't have an answer to that question yet. Okay. Likewise, what if your domain is a curve in space? Or, weirder, what if your domain is a surface in space? Right? This is all very weird. Now, why might you want to do, what are the real world applications to these kinds of things? And when will I ever need to chop it up, add it up on an interval? Well, maybe you're trying to compute the mass of a bent wire, either in 2 dimensions or in 3 dimensions, right? Some bent wire. You want to compute the mass of it. Maybe you want to compute the center of mass. Maybe you want to compute the moment of inertia of some bent metal wire, like that. Right? Tough. Those are chop it up, add it up kind of questions. Hey, maybe there's a bunch of ants running around on the surface of this wire, and the ant density, ants naturally gravitate to higher altitudes for whatever reason. Maybe there's a heat lamp up there, right? And so the height tells you the ant density. Maybe, I don't know. Right? Chop it up, add it up. Maybe you're looking at a side of a mountain. That'd be a weird shaped mountain, but you could imagine a surface, right, that is the side of a mountain, something like this, and maybe there's some weed growing on the side of the mountain, and the weed density, how much weed per unit area is lower at higher altitudes. Well, here we have to chop it up, add it up, but again, we have this dimensional awkwardness. So the first thing we have to do is just recognize, okay, these are dimensionally different. These are not double integrals. They're not triple integrals. And so we just got to write down new Riemann sums. That's all it is. No big deal. Nothing to be afraid of. Right? On a curve, for example, that one, I can talk about chopping it up into little pieces. And I'm going to sweep away all the rigor and the formalities and the regularity concerns, and that's not what we're interested in Math 212. You can talk about chopping it up into little pieces, and then on each little piece, talk about, how much of whatever it is that I'm interested in, how much is there on that little piece, on that little piece, the amount of whatever it is that I'm interested in is going to be the size of the piece, namely length, right, multiplied by some appropriate, stuff per unit length, right? Some appropriate notion of density to that problem. I mean, if I'm counting ants, well, I need to know how many ants per unit length. What's the ant density at that location, right? And likewise for other things. So punchline, you add that up over all the little pieces, etc. And here's a chop it up, add it up formula. It's basically a Riemann sum. Right? And what do we do with Riemann sums? Well, we call them integrals, right? So we say integral of whatever that function is, ds. So, very believable notation, and we have now defined something called a line integral. Yeah, new kind of an integral, different Riemann sum. We have not written down these kinds of integrals before. Likewise with surfaces. So, up here, if you have some surface in space like that, well, same deal. If you have a surface in space floating around like that, you can chop up that surface into little pieces. And if you're counting the total number of a certain kind of, a certain kind of grass, or a certain number of maybe ants again, maybe ants are swarming all over this hill, what have you. The grand total number of ants is the sum of how many ants are on each little piece of area. On each little piece of area, the area times ants per unit area, right, whatever your appropriate density is, tells you ants, right? The grand total number of ants in that little piece is that product. Add up over all the pieces, and you've got yourself a new kind of an integral. Now, we have no idea how to compute these things, right? All I'm doing so far is writing down notation to suggest the idea that, look, we're chopping up these weird domains, and then we're analyzing the question at hand on each little piece that I've chopped it up into, and then I'm adding up over all the pieces. How do we actually compute these? Oh my gosh, totally different question, right? But integral, right? ds. And this is what we call a surface integral. Okay. How are we doing? Everybody on board? Everybody willing to believe that we can do chop it up, add it up on weirder shapes? Okay. Now let's deal with the elephant in the room. Yeah, but these are weird shapes. I don't know how to do. What are my bounds? Can I just write down an iterated integral? Can I do an iterated integral on this? How do I actually turn the crank and get answers? Right? I'm an engineer. I need to build something. I need to know the numbers. Okay. Well, there's a great trick here, which is I'm going to call this an undesirable domain. Let me remind you, we already have a technique for how to deal with undesirable domains. Change of variables. Right? With change of variables, the big idea was take your undesirable domain. Maybe it's got corners and, it wraps around in weird ways, whatever. View it as being an image. If you can make your undesirable domain an image of something, then you can pull back, keep track of your stretching factor, and off you go. Right? Okay, so that's what we're going to do. We're going to view this as being an image of a nicer domain, details to come on the next page, and then pull back in stretching factor. Okay, so let's start with a curve. Here's my undesirable domain. I mean, it's not a Calc 1 integral domain. It's not a double integral domain. This is an undesirable domain. It's dimensionally awkward. I don't know where to get started, right? But how about if I can view it as being an image, then I can do a pullback. Now, this is one-dimensional. It's a curve, so I appeal to your geometric intuition. I should be able to make it the image of an interval. Right? I like this domain. That domain's awesome. That's an interval from A to B on the t-axis. That's Calc 1. That's a great domain. Right? So what I need to do then is to figure out how can I view a curve as an image. And this may just ring a bell, right? Flashback to chapter 12. We talked about this stuff. This is a parametric curve. We've already done that. We've already viewed curves as being images of functions from some, we didn't say pullback domain, we didn't say stretching factor at the time, right? But nevertheless, parametric curves give the curve as an image. So that's great news. We've already got this construction. All we got to do now is figure out what that stretching factor is, which also not that big of a deal. The way we're going to understand, this little bit of curve. Now let me blow up. It's just hard to see on that teeny tiny little picture that I have there, right? So I'm going to blow that up larger. Here's my little piece of curve. I want to understand that piece of curve. I'm going to do so by way of this vector here called the dx vector. We talked about the dx vector way back in chapter 12. It's our position differential, right? This is the x function, right? And this is our estimate of how much position, where I am on the curve. This is my linear estimate of how much my position on the curve changes. It's not exactly how much my position changes, but I actually went to over here, but my linear estimate based on linear understanding of what's happening to the position function, my linear estimate would have me over here. So this dx vector is that position differential. It's got coordinates. Dx scalar and dy scalar. Those are really easy to understand. Dx is dx dt times dt, old Calc 1 fact, right? Again, there's that temptation to do that. Again, we're not really going to do that, but it feels like, right? So there's your dx scalar. Here's your dy scalar. So these are easy to calculate. Those are just keeping track of how a single output variable changes as you change a single input variable t. Right? Well, then, good news. The dx vector that I'm trying to understand has components, which are the dx and the dy that I just wrote down formulas for. The ds scalar that I'm interested in, this length of that piece of curve, is the magnitude of that dx vector in purple. And, crunch it out algebraically, and the final punchline is, v dt. So this is ds. Let me go back up to this picture here. If I want to know how long is that little piece of curve that I've expanded to there, that little piece of curve, ds, it's v times dt, dt being this little length over there. And notice I have output size now as something times input size. You can see on the pullback picture over here, right? We've got output piece is a stretched out version of that input piece, and you can see that stretching factor. Here it is. That stretching factor is speed. Okay, now we could have gotten to this result much more easily in a different way. Let me show you the easier way to see this, just for sort of geometric satisfaction. Do you all remember from high school physics class or high school, physical science or whatever they call it, but distance equals rate times time. That's hopefully pretty satisfying, right? So it's good to see it that way also. Distance equals rate times time. So that's all well and good. I do want to note here, though, that this process of finding the stretching factor by studying the position differential, that's something that we're going to do in other contexts in ways where we don't have an easy way out like that, right? So what I'm doing here by doing this the hard way is I'm laying some groundwork. Okay. All right. Okay. So there you go. Now the book makes what I consider to be a curious decision here. It's not it's not that bad, but the curious decision. The book now has a formula for how to compute everything that we need in here. And rather than do examples and applications, etc., they punt and do that later in the next chapter. And then they move on to they move on to surface integrals here. I don't know. I think whatever. That's fine. So we're actually going to do, as the book does, we're going to do surface integrals next. But I wanted to point out that, well, line integrals are really a natural segue into the surface integrals question. And look how similar the story is going to be. I can view a surface. Oh, that was terrible. Let me try that again. I can view a surface as being an image and have kind of already got that concept. I'm just viewing position, right, x, y, and z, as functions of two variables, u and v. It's the same idea. It's the same idea as a parametric curve. It's just now we're trying to describe a surface, and so we're going to need a two-dimensional pullback called a parametric surface. Same idea as a parametric curve. Okay. I've got this domain that I don't like because it's dimensionally awkward. I want to pull back to this domain that I do like because it's dimensionally natural. It's a two-dimensional thing in a two-dimensional world. I therefore need to study a little piece of area and the size of its image. Let's expand those to make them a little larger. I've got this little piece of area over here, this little rectangle, and I need to look at its image, which is going to be approximately a little parallelogram. It's going to curve a little bit. It's a surface, right? But it's going to be approximately a parallelogram. We're going to understand that by looking at this edge vector and trying to understand its image edge vector. And then we're going to look at that edge vector and we're going to try to understand its image edge vector. And once I understand those edge vectors, I can compute the area of that actual parallelogram, and I can use that as a way of understanding the area of the approximately parallelogram sort of underneath it. Details to come next time after spring break. So y'all have good spring break and relax. Try to stay healthy. And be on the lookout for emails possibly from me about Duke's reaction to the health scare situation, if any. But anyway, see y'all later. Have a good one.